All right, we're going to start our next problem here. And so for this problem, we're going to get, if you look what this says, we're going to get the shear as a function of uh, distance along the beam. So we're going to set up a coordinate system starting right here. This will be 0, and we're going to move across. All right. This beam is 11 meters long, and I have here's a pin joint. Then I have 8 meters of 40 kilonewtons per meter. That's 320 kilonewtons total. Here I have my expansion joint. So that's just a vertical support here. Then I have 3 meters with nothing, but on the end, we have 20 kilonewtons applied right to the end for whatever reason. And right here, we have 150 kilonewton meter torque that's applied. And if you look at that, it's trying to pinch the bottom. Okay? So we're going to go all along and we're going to plot shear and bending moment. Now, given the idea of computing these things from the problems we've done thus far, it's fairly simple at any given point to figure that out. But now we have to do this everywhere. So it may look a little daunting to you. All right. But we do all these problems basically the same way. We're going to start to see there's a real pattern to these things, and we're going to find we can take some amazing shortcuts. So let's just see where we get to. So we need to figure out first the supports. This is always step one. Free body diagram. Pin joint, there's no forces in the X, so this is the only place where an X force could be to counteract that. Don't need it. So we have a vertical force at the pin. We have 4 meters, then 320. That's based on the center of mass, as it were, of this distributed load. 4 more meters, then bam, we have our vertical support. 3 meters, and then we have the stuff applied to the end for whatever reason. It was applied. This is an educational. This is for education, so we can do things like that. All right. I would sum the moments here at A in the usual way. So summing the moments at A, they must equal 0. I have 320 times 4 going this way, B8 going the other way, plus BY times 8. Then I have 20, that's 11 meters out clockwise. And then this is clockwise as well. Solve for BY, I get 206.25 kilonewtons. Summing the forces in the Y, knowing this is 206.5, straightforward, you wind up with AY is 133.75 kilonewtons. All right. So given all that we've done with rigid body equilibrium, this should at this point be really easy for you. There's nothing much there. So now we're going to start going into the procedure for handling this. And here's what I recommend you do. All right. The first thing we're going to do is we're going to evaluate what's happening with the shear and bending moment at this end and at that end. To do that, we're going to blow it up, but we're going to envision taking an impossibly small sliver of beam, 0.0000001 meters of beam, and we'll do it over here. And we're going to find out by doing that, because it's such a small sliver, we're going to figure out the shear and bending moment at the front and at the back, as it were, of this beam. And then we're going to put them on the plot, all right? And then start working our way across the beam to see what we get. Now, so as we go, we're going to work our way across the beam, and here's the thing. If we don't match, we are going to independently assess these front and backs from the process we do across here. So what's going to be nice about this is as we build this thing up as we walk across, if we match the end number we have here, we'll be self-checking. All right, so this is how we check ourselves. If we don't get, by going across the beam, come to the same number we're going to come to in just a moment, we'll know we made a mistake. Now, this doesn't tell you where you made a mistake, but you will know at least you made one. That's a huge piece of knowledge. All right, so we're going to evaluate the ends. All right, so here's what I'm doing here. All right, left, right. Notice here I have a lot of zeros, 1 meter. So this is impossibly small. All right. So here at this support, we had 133.75 kilonewtons. Let's make this a little bigger. Okay, really, really, really small distance. And here is a distributed load. So 40 kilonewtons per meter times an unbelievably small amount of meters. What is that number? 0. If I made this small enough, that's 0. All right. And then I've cut the beam, so everything to the right I've thrown away. So here I put in, this would be the shear at 0, because this is the 0 point along the beam in terms of x. And I have positive bending moment trying to pinch the top. So I have 133.75 kilonewtons coming up, no load on the top. So that tells me the shear, simply 133.75 to start. This was positive, it would take it clockwise. I got a positive number here, so I have positive shear to start. Now, what's the moment? If I were to sum the moments, it doesn't matter where we do it. Let's just sum the moments here. Put a great big dot in here. If I sum the moments here, this force times this impossibly small distance gives 0 moment. So how much bending moment do we need to offset that? 0. So shear is 133.75 positive. Bending moment is just plain 0. Not positive, not negative. Let's go to the end. Same game. This is 0.0000001 meters. It's so small, you can't see it. All right. Here's 20 kilonewtons coming down in the end. Here's this 150, basically pinching the bottom. On the other side of this impossibly small beam, I have shear going up because that's trying to go clockwise. That's positive shear. This is trying to pinch the top. Some forces. This is 20 kilonewtons down. Ooh, this needs to be 20 kilonewtons up. So it is very apparent. Over here we had, this is 133.75. It's visually obvious summing the forces. Here it is visually obvious 20 kilonewtons. So we're starting at positive shear. We're ending at positive 20 kilonewtons shear. All right. Now, sum the moments. All right. We have a moment here. Now, if we take the moments, let's say we take them right here, because this distance is so impossibly small, this produces no moment right here. So we ignore it. This is located at this spot. Ignore it. So what I have here, when I sum the moments, all right, just bring this down. This is pinching the bottom. All right. Therefore, this needs to pinch the bottom. If I do this as an equation, I would have summing the moments right at that spot. Summing the moments, set it equal to 0. This is clockwise, so I have a minus 150. That's clockwise. So I have minus, I'll just call it MB. All right. Sum. You wind up with MB equals minus 150. So this, I assume this direction is telling me it has to go the other way. Well, that makes sense. If this side is pinching the bottom, then this side has to pinch the bottom from the other side to balance that out. This one's clockwise, that one will wind up being counterclockwise. Now, note I drew this in based on pinching the top is called positive on my plot. All right. This force, what we just found, oh, wrong word. This moment is minus 150. Physically, it is going this way. So in the world of vectors, that's counterclockwise. That's positive in the vector world. But in the bending moment world, pinching the bottom is negative. You have to keep that straight. All right? So now that we have these, we know that we've gone through. So we always draw these things in based on positive shear and bending moment and let the signs fix themselves. This says it's negative. Fine. There we have it. So now I take these. This is the next step of the process. I'm going to move this over here. I'm going to give ourselves a bigger field of view. All right. And here is our plot. Oh, we'll just show this. This shows, we'll make this bigger for just a moment. Shear as a function of x, going from 0 to 11. It's in kilonewtons. So notice what I have here. At 0, I've got a dot I put in. This corresponds to 133.75. At the end, here's a dot for 20 kilonewtons. Down here, I have bending moment. All right. M sub B, where B stands for bending moment, is a function of x in kilonewton meters. It goes from 0 to 11. And here I have a big dot starting at 0. And we said at the end, we're going to stop at minus 150. We'll add the unit. Kilonewton meters. So now we're going to do the plot, and we hope we end up here, and we hope we end up there. If we do, we'll have checked our work. All right, so we're just going to, as we do our work, what we're going to do now is we're just going to come back to this plot. All right, so we've done everything we need here. The only, as we work our way across, we will remember that this force here is 206.25 kilonewtons, and if we need to, we'll just come back to the picture. All right, so notice what we have as we go across. We have 40 kilonewtons per meter. Then we're going to have this 206.25 come up, then nothing, and so forth. But I can only show so much in the camera, so I'm going to let that disappear. All right, if you go online, that information is available to you. You can print out those pages and have them for yourself right now. All right, so now what we need to do is back here was point A, all right, that force. Here that is. So this is a free body diagram, and I'm going to go right back to this right away. So what I'm going to do is I'm going to find shear and bending moment as I go across the beam. So picture I'm just walking across the beam from 0, which I figured out already. It's 133.75. Okay, and I'm going to go up to 8. Why do I stop at 8? Because for two reasons. The distributed load stops at 8 meters, and then I have this support. So I need to then reset my equations at this point. So I'm going to draw one free body diagram that allows me to go from here right up to the edge here. So that's what's happening. And then we'll plot the result as we go. So there's our plot that we're working on. And now here's the free body diagram for our beam. Okay, so let's look at what we have. So starting from A, so here's the support, 133.75. I have some distance x of beam, where x is between 0 and 8, where the support is, where both supports are. So it's in between there. I go out some arbitrary distance x. I throw away all the beam to the right. I have a shear that would take this thing clockwise and a bending moment that pinches the top. In that region, I then have a distributed load of 40 kilonewtons per meter. So the total force is 40 kilonewtons times however many x meters I have here. Here is, and this will be, since it's uniform, it'll be in the center. So I have x over 2 distance here, x over 2 distance there. All right. So now I'm going to sum forces, sum moments, and we're going to figure out what is the shear as a function of x in this region, and what is the bending moment as a function of x in this region. Okay? All right, so summing the forces in the y, it's fairly straightforward. So we have 133.75, that's it, minus 40x, and then minus shear as a function of x. All right, well, I can solve for that. B of x is 133.75 minus 40x. We have it right there. And in fact, I can, if I wanted to, I can actually I'll just kind of go over here and note 133.75 minus 40x. I can set that equal to 0. And so what you see here is as I go along, the shear is going to be, this is subtracting. So I'm starting at a shear of 133.75. And if I go 1 meter out, it'll be minus 40, so it'll be at 93.75. It's going to be dropping. And there'll be a point where it goes through 0. So that would be useful to know for my plot. So if I solve for x, I would come up with 3.34 meters. Okay, well, that's fairly easy. So there's another thing I want to notice. Okay, I can rewrite this the following way. This is the initial condition that I started with. That was the initial shear. I'll call that VIC plus, okay, I have a distributed load here. I'm going to let that, we normally call that an omega. And so if I look at what I have then, this is the integral of the distributed load dx, where omega is minus 40. So I had that 40 kilonewtons per meter all along here, and this equation says what was your initial shear, and then just integrate the distributed load as you go across. This is always the case. All right, and I'll put units on that. All right, so there we have that. Now, we can go, let's just take the moment part first. So let's sum the moments. All right, I'm going to sum the moments right here because that'll eliminate the V term. I always do that. That's just my practice. So I do that. So I have this force, a distance x, that's going clockwise. So I'm going to have minus 133.75 x here. All right. Then I have this force. It's 40 times x, which is x over 2 away. That's going to go counterclockwise. So I have plus 40 times x over 2. So I have that. All right. And then this is going counterclockwise. So I put a plus mbx. All right. Now I'll just solve for mbx. mbx is equal to, so this is already positive, so I'll move everything to the other side. So I'll have 133.75x minus 40x squared over 2. And take a look at this. So here's the shear. Here's the bending moment. Look at this. Look at that. The bending moment is the integral of the shear. This is always the case. So once we figure out the shear, all we have to do is integrate it. So we can write this little equation, kind of cute, as mb, bending moment, initial condition, plus the integral over the range we're looking, in this case 0 to x, v of x dx. We can just integrate this thing. All right? And this is really simple. Notice that while this is an integral here, it was just uniform, so we could actually have done this part in our head. And then once we have this equation, that's just really straightforward to do. All right. So what we're going to do now is let's plot this thing. All right. So we're going to go in shear from 0 to 8 meters. All right. So let's see. We're going to drop, all right, 40 times 8, 320. So here we were at 133.75. We're going to linearly drop 320, okay, 320 kilonewtons. Well, that works out to, let me just do it. It's a far easier way to go. 1, 2, 3. We know we go through 0 at 3.34. That's right around here. All right. And let me go down another unit of distance. That'll take us to minus 200. And I'm just going to draw a dotted line here for myself. Okay, so if I subtract 320 from this, I would come up with minus 186.25. So I'll just draw this in. And notice how everything just kind of lines up pretty nice. Goes right through where we said it should go through. So notice this is linearly losing shear. So it starts here, drops down. All right, so that one's done. Now, we need to, this is the integral of that. Well, that sounds kind of complicated, actually. So let's see that. If this is the integral of that, it says this is the slope of this. So if this is the slope of that, and this is the integral of that, since this is slope, the slope here is 0. So this spot's like really important. So we're just going to put a straight line going down. Something's happening there. So if you look at this, slope here is positive, so it's going to come up, and it's going to level off here, and then it's going to start going down. So here's what we can do. This is kind of slick. I can just go and look at this triangle right in here, and I can get the area of it. So it's 133.75. It's 3.34 long, because that's the where it goes through 0. We know that. Move that over a bit. And divide by 2, because it's a triangle. Well, that number is 223.61. So since that's the integral of that, so I need 223.61. So let's see, that's this goes up at 80, so there's 200, 223. That's right about here. All right, so if you want something more accurate, get a computer to plot it. So this has 0 slope, so it's going to be kind of rounded off. And so we can do something kind of like this. And rounds off. Pretty good. All right, now we have this piece to look at. So I have this triangle down here to look at. So I can see this goes, the depth is 186.25. This distance is 8 minus 3.34 divided by 2. All right, that is 433.61. So that tells me from here, I need to draw 433.61. So let's note that this one is 223.61. And I'm going to drop 433.61. All right, so that says I'm going to drop, let's see, here's 200, there's that, minus 210 would take me from there to there. And so we'll just give a reasonable artist's interpretation, so falling off like that. Close enough. All right, this is a sketch. If you want something more accurate, use a computer. These are easily computerized. We're just looking to pop a sketch and basically understand what's going on. All right, so now we're going to move on to the next piece right here. Okay, so here we have my free body diagram. Here was A. All right, I'm now going through 8 meters where I have 320 kilonewtons of force from the distributed load. Then we go through our support. That was 206.25. And now X is going to start at 8 and go from there. At the end, I have my shear. So I'm going to cut it off as I make my way out to 11. Shear goes down for positive, and I try to pinch the top. All right. So now we just do a sum of forces. And so we have 133.75 up. Let's leave that there. Minus 320 down, plus 206.25 minus V. solve for V, and it's 20 kilonewtons. All right, so let's just go directly and plot that. We go over here at 20, boom. So let's see, we were at minus 186.25, and look at this. We went through a 206 kilonewton force, and we went up 206 kilonewtons. This is interesting. So we started here at 133.75, and as we went through 320 kilonewtons of force, the shear dropped 320 kilonewtons. We then, in one point, in an instant, we went through 206 kilonewtons, shear jumped 206 kilonewtons. Force down, shear dropped. Force up, shear up. This is always the case. So what it means is we can actually walk across the beam as we see a force, whether it's distributed or at a point. As the forces go down, shear goes down. Figure out your initial point, and then just add on to that. As force goes down, drop. As force goes up, go up. Whoop, whoop. So we went up here, and then we added on 206.25. That was that amount. Bam, we're at our 20. We matched the endpoint. We checked. We know we're good. Kind of neat. All right. Well, now let's see what we have here. We need to get the bending moment. Now, if we could use our integration trick, all right, it says the area underneath the shear, we have 20 kilonewtons over 3 meters. That integrates out to 60. And it's linear. We keep getting even amounts of area. So that says that what we should get is this. That would take us to our 150. We'd hit the point we wanted, and zip, bam, boom, we'd be right. Does the math agree? Let's find out. All right, so we're going to take the moments, as I always do, right here at the point that eliminates the shear. So I have this relative to that, that's clockwise, so I have minus 133.75x. All right, move this over so I have some room. Now I have 320, okay? So that distance is going to be x minus 4, right? From here to here. So I have, this is going counterclockwise, so 320 x minus 4. Then this distance, from here to here, this is going clockwise, that's x minus 8. So minus 206.25 x minus 8. And then when I get out to here, this is at the point, it does nothing. This is going counterclockwise, so I just put in a plus mb. All right, and it's a function of x, so I can leave that there. All right, if you were to reduce this down, you would find the following. mb as a function of x is, multiplying all this out, you will come up with the following. Minus 210 plus 20 x minus 8, which is exactly, notice minus 210 here, which is exactly the initial condition from where we started, plus the integral of 20 going from 8 until x dx. This is that. It's the same, and you would get the same thing every single time. So there, we've already finished our drawing. So what we now have is a process by which we can actually walk across a beam, and as we figure out what the endpoints are, and we'll figure out the endpoints for the bending moment. We get our initial conditions. And then all we need to do is walk across this beam as force goes up or down, go up or down on the shear, and then integrate this picture, and we got all the moments, and we never had to write any of these stupid equations. That's really slick. So let's just take a quick moment. This has been a very long video, but I don't know any way to make it shorter. So, and let's just see what our observations are. What can we learn from this problem? Well, quite frankly, a whole bunch. Here's our observations. shear, we simply integrate the distributed load. All right, here was the shear, the equation for the shear, it's just the distributed load integrated. This is always the case. As we go across the beam from left to right, force goes up, shear goes up, force goes down, shear goes down. Always the case. Here's the basic equation. Shear as a function of x is the initial condition where the distributed load starts, and then just integrate the distributed load, adjusting the x's as you go. The distributed load could go up, that would make that positive. Or if the distributed load is going down, then a negative sign goes in there. No problem. Take this, integrate it. So the bending moment is simply your initial condition, where you're looking to start analyzing the beam, plus the integral of the shear, adjusting for where you are in the x along the beam. Here's the neat part of this. The process of walking across the beam is completely independent of how we computed our end conditions, namely the end condition on the right at x equals 11. If the process of walking across the beam using this matches up the end condition when you get to the right, this thing, you have a completely independent self-check. If they match, you know you're right. The problem is over. This is one of the few things in engineering, if you follow the procedures, you know you're right. When you get to the end, you also know if you made a mistake. Doesn't tell you where, but that's a huge piece to know you even have a mistake. All right? So what is our procedure? I didn't put free body diagram in here because that's part of getting the supports, but it's there. Free body diagram. Get the supports. Figure out what's happening in the ends with shear and bending moment with an impossibly small piece of beam. Then simply walk, what I will call this is walk the beam, applying the following equations that are basically amounting to if force goes up, shear goes up, force goes down, shear goes down. Then integrate the shear to get the bending moment. And you can do this all graphically. All right? That's the end of this one. We're going to practice a whole bunch of these. I'll see you again soon.